In my today's lecture, I want to discuss the wind machine, the history of wind machines and mills, and the classification of wind machines and mills. The history of wind machine and mills. The first known use of wind dates back 5,000 years to Egypt, where boats used sails to travel from shore to shore. The first true windmill, a machine with vanes attached to an axis to produce the circular motion, may have been built as early as 2000 BC in ancient Babylon. By the 10th century AD, the windmills with wind-catching surfaces having 16 feet length and 30 feet height were grinding grain in the areas in eastern Iran and Afghanistan. The earliest written references to working wind machines in Western world date from the 12th century. These too were used for milling the grain. It was not until a few hundred years later that windmills were modified to pump water and reclaim much of Holland from the sea. The multi-vane farm windmill of the American Midwest and the West was invented in the United States during the latter half of the 19th century. In 1889, there were 77 windmill factories in the United States, and by the turn of the century, the windmills had become a major American export. Until the diesel engine came along, the many transcontinental rail routes in the US depended on large multi-vane windmills to pump water for steam locomotives. Farm windmills are still being produced and used, though in reduced numbers. They are best suited for pumping groundwater in small quantities to livestock water tanks. In the 1930s and 1940s, hundreds of thousands of electricity producing wind turbines were built in the US. They had 2 or 3 thin blades which rotated at high speed to drive electrical generators. These wind turbines provided electricity to farms beyond the reach of power lines and were typically used to charge storage batteries, operate radio receivers, and the power a light bulb also. By the early 1950s, however, the extension of the central power grid to nearly every American household via the Rural Electrification Administration eliminated the market for these machines. Wind turbine development lay nearly dormant for the next 20 years. Now the classification of wind machines and mills. Wind turbines are classified into two general types. Number one is horizontal axis and number two is the vertical axis. A horizontal axis machine has its blades rotating on an axis parallel to the ground as shown in the figure. A vertical axis machine has its blades rotating on an axis perpendicular to the ground as shown in the figure as the vertical axis wind turbines. Three-bladed rotors operate more smoothly and generally more quietly than the two-bladed rotors. Visually, the three-bladed turbines rotate smoothly, but two-bladed turbines may appear to wobble. Single-bladed rotors with a counterweight have been field tested at full scale, but the asymmetry produced too many difficulties for the commercial prospects. So now come to the wind machine mills as the horizontal axis wind machines. This is the most common wind turbine design. In addition to being parallel to the ground, the axis of the blade rotation is parallel to the wind flow. 2 and 3 bladed horizontal axis wind turbines are by far the most common for electricity generation, with the rotor consisting of both the hub and the blades. Here the figure shown the single bladed horizontal axis wind machine, 2 bladed horizontal axis wind machine, 3 bladed and the multi bladed. Gearing and the generators are usually at the top of the tower in a nacelle. Multi-blade rotors having large starting torque in light winds are used for water pumping and other low-frequency mechanical power. All wind turbines have the blades similar in operation to airplane wings and also but less so to the airplane propellers. Actually, the dominant driving force is lift, as shown in the figure. The figure shows a blade section of a horizontal axis and wind turbine blade. The same principles apply to the vertical axis turbines. The front view A describes the front view of the horizontal axis turbine blade rotating the section speed at V. Figure B is the perspective view showing the unperturbed wind speed U0, and the figure C shows the details of the airstream velocities and forces at a wind turbine blade section. The unperturbed wind speed U0, relative wind speed VR, this is the VR, this is the unstripped wind speed U0. The blade setting and the pitch angle is the gamma, and the angle of attack is called the alpha. Inflow angle, that is called the phi. Phi is the inflow angle, and the blade is rotating at the omega radiation per second at the right angles to the upstream wind direction. Okay, the blade tip moves at the tip speed v is equal to r omega in the plane of the rotor at the right angles to the upstream wind direction. This is the lift force and this is the drag force. So the section is rotating approximately perpendicular to the distant oncoming wind of the speed u0, and because of its own movement, the blade section experiences on the coming air at the relative velocity vr. So as the air is perturbed by the blade, a force acts which is resolved into the two components. One is called the drag force. Fd is the component in line with the relative velocity Vr, in line to the relative velocity Vr. So this is the relative velocity and this is the drag force. Another is called the lift force, that is Fl, is the component perpendicular to the Fd. This is the lift force. Okay. The use of the word lift does not mean that the FL is necessarily upwards and derives from the equivalent force on an airplane wing. So the next step are to resolve the split both FL and FD, that is called lift force and drag force. First step is along the axis of the rotor with the sum of resolved components being the overturning axial thrust, that is called F thrust. Because of drag is small due to the smooth aerodynamic surfaces and lift is maximized from the shape of the airfoil, the net force in the plane of the rotor F rotate is in the direction of rotation. So F rotate is the direction of rotation. F rotate. This is the F thrust, axial thrust. Second is in the plane of the rotor with the algebraic sum. Actually they are difference in magnitude since the resolved components have opposite direction, so there should be the algebraic sum. So being the rotational force, that is called F rotate. The force F rotate turns the shaft of the turbine and enables the power to be extracted from the connected generator. Some machines are designed to operate in an upwind mode with the blades upwind of the tower. In this case, a tail vane is usually used to keep the blades facing into the wind. Upwind turbines need a tail or some other jawing mechanism such as electric motor drives to maintain the orientation. Here the figure shows the upwind with the fan tail passive steering. This is the upwind with the active steering from the side rotors. This is the upwind with the active power steering switched by wind vane. This is the downwind self-oriented or power steer fan. The other designs operate in a downwind mode so that the wind passes the tower before striking the blade. Without a tail vane, the machine rotor naturally tracks the wind in a downwind mode. So the downwind turbines are in principle self-orienting but are more affected by the tower, which produces wind shadow and extra turbulence in the blade path. The turbulence of this kind cause the cyclic stresses on the structure, additional noise and the output fluctuations. Upwind and downwind machines of rotor diameter of more than about 10 meter use the electric motors to control the jaw. Some very large wind turbines use a motor-driven mechanism that turns the machine in response to a wind direction sensor mounted on the tower. Although the vertical axis wind turbines have existed for centuries, they are not as common as their horizontal counterparts. The main reason for this is that they do not take the advantage of the higher wind speeds at the higher elevations above the ground as well as the horizontal axis turbines. Commonly found the horizontal axis windmills are aero turbine mill with the 35% efficiency and the farm mills with the 15% efficiency. Now come to the vertical axis wind turbines. By turning about a vertical axis, a machine can accept the wind from any direction without adjustment, whereas a horizontal axis machine must jaw. An expectation for the vertical axis wind turbine generators is to have the gearboxes and generators at the ground level. A vertical axis machine need not to be oriented with respect to the wind direction. Because the shaft is vertical, the transmission and the generator can be mounted at the ground level, allowing easier servicing and a lighter weight, lower cost tower. Although the vertical axis wind turbines have these advantages, their designs are not as efficient at collecting energy from the wind as are the horizontal machine designs. There are several types of vertical axis wind machine mills are there. First is the cup anemometer. The anemometer is an instrument for measuring the speed of airflow. A cup anemometer is a drag type vertical axis wind turbine. These are the cup type anemometer. The shape of the blade is a cup shaped. This device rotates by the drag forces. The shape of the cups produces a nearly linear relationship between the rotational frequency and the wind speed, so that the measurement of the number of rotations per time period correlates to average wind speed over that period. Second is the Savonius rotor, that is turbo machine. There is a complicated motion of the wind through and around the two curved seed airfoils. The driving force is principally drag. This drag type vertical axis wind turbines turns relatively slowly but yields as high torque due to the large solidity. It is useful for grinding the grain, pumping water, and many other tasks, but its slow rotational speeds make it unsuitable for generating the electricity on a large scale. The construction is simple and inexpensive. This type of wind turbine, invented by S.J. Savonius, is a vertical axis machine consisting of two half cylindrical blades arranged in S shape as shown in the figure. S shaped. Convex side of one of the half cylinder and the concave side of the other are facing the wind at a time. The basic driving force of the Savonius rotor is the drag type, which I already told. The drag coefficient of a concave surface is more than the convex surface. Hence, the half cylinder with concave side facing the wind will experience more drag force than the other cylinder, thus forcing the rotor to rotate. Sometimes two or more rotors fixed one over the other at 90-degree offset may be used to smoothen the torque fluctuations during the rotation. Another way to improve the performance is to attach the deflector augmenters with the rotor. Being the drag machines, the Savonius rotor have relatively lower power coefficient. They work at low tip speed ratios with the maximum of about 1. They are very simple simple in construction, even can be made from well barrels cut in two halves lengthwise. It is not suitable for electricity generating wind turbines due to its low tip speed ratio and its comparatively low power coefficient. With an optimized aerodynamic design, the Savonius rotor can also make use of aerodynamic lift, and its maximum power coefficient is then of the order of 0.25. Now come to the third type of vertical axis wind machine, that is Darrieus rotor. The Darrieus rotor turbine is the most famous vertical axis wind turbine. It is characterized by its C-shaped rotor blades, which gives it its egg beater appearance. This is like in the figure, shown in the figure. This is a egg-shaped structure. The blades are in C-shaped. It is normally built with 2 or 3 blades with an airfoil section. The typical blade configuration helps in minimizing the bending stress experienced by the blades. Darius rotor usually works at high tip speed ratio, which makes it attractive for wind electric generators. They are not self-starting and require external excitation to cut in. The rotor produces peak torque only twice per revolution. The rotor shape is a catenary with the aim of the rotating blades being only stretched along their length. Unlike the Savonius wind turbine, the Darius is a lift type VAWT. It uses the lift forces generated by the wind hitting aerofoils to create the rotation. Now the fourth one is the Musgrove rotor. The blades of this form of rotor are vertical for normal power generation, but tip or turn about a horizontal point for control or shutdown. There are several variations which are all designed to have the advantage of fail-safe shutdown in strong winds. The Musgrove rotor was developed by a research team under Professor Musgrove at the Reading University, UK. The production cost of these systems are still so high that they cannot compete with the horizontal axis rotors. The H rotors or the horizontal rotors of a particularly simple structure with the permanently excited generators integrated directly into the rotor structure without intermediary gearbox. Now the last one is the cyclo-gyro windmill. The gyro mill is typically powered by 2 or 3 vertical aerofoils attached to the central mast by horizontal supports. Gyro mill turbines work well in turbulent wind conditions and are an affordable option where a standard horizontal axis windmill type turbine is unsuitable. Another variation of the gyro mill is the cycloturbine, in which the blades are mounted so they can rotate around their vertical axis. This allows the blades to be pitched so that they always have some angle of attack relative to the wind. The main advantage of this design is that the torque generated remains almost constant over a fairly wide angle. So a cycloturbine with 3 or 4 blades has a fairly constant torque. Over this range of angles, the torque itself is near the maximum possible, meaning that the system also generates the more power. The cycloturbine also has the advantage of being able to self-start by pitching the downwind moving blade flat to the wind to generate the drag and start the turbine spinning at a low speed. On the downside, the blade pitching mechanism is complex and generally heavy, and some sort of wind direction sensor needs to be added in order to pitch the blades properly. For the Darius and the Musgrove rotors, the driving wind forces are lift with the maximum turbine torque occurring when a blade moves twice per rotation across the wind, so pulsing the rotation. Uses are for electricity generation, and the rotor is not usually self-starting, so may be initiated with the generator operating as a motor. Now come to the advantages and disadvantages of the vertical axis windmill. The advantages are the VAWT can receive the wind from any direction. The generator and the gearbox of such systems can be housed at the ground level, which makes the tower design simple and more economical. The maintenance of these turbines can be done at the ground level. The pitch control is not required when used for the synchronous applications. The disadvantages: the VAWTs are usually not self-starting. The additional mechanisms may be required to push and start the turbine once it is stopped. As the rotor completes its rotation, the blades have to pass through the aerodynamically dead zones, which will result in lowering the system efficiency. The blades may run at dangerously high speeds, causing the system to fail if not controlled properly. Wires are required to support the tower structure, which may pose the practical difficulties. Now these are the references from which I make these tutorials. You may go through these reference books and websites. Thank you.